Hello. So this is a lecture for UCSF Biomedical Imaging 201 Principles of MRI. And this is some optional material, but that I wanted to present as a supplement to some of the information that's in Chapter 2 of our textbook, MRI the Basics. A little more focusing in on some of the principles of creating and detecting magnetic fields. Since we talked a little bit about particularly RF coils and also the creation of main magnetic field that this is relevant to. So as a brief refresher, magnetic fields, they exist everywhere. They have an amplitude and a direction. So therefore, they're a vector field. In other words, they're at every point in space, you can represent the direction of the magnetic field by a vector, the direction and an amplitude. In most general notation, we could say this magnetic field B that has three directions, Bx, By, Bz, exists at all points in space, x vector, which is x, y, z, and it can also change over time, which is certainly something we will do a lot of in MRI. And how do we create magnetic field? Well, we have some very simple ways to create magnetic fields that we'll use a lot. And the main one of these is looking at currents in loops of wire. So that's what's illustrated up here, is that if you take a loop of wire, you run a current through this loop, you can use now this becomes a right-hand rule from physics. Use a right-hand rule, and that's going to create the current, will create which is an electric field, will create a magnetic field in the perpendicular plane, like so. And so the current I creates this magnetic field B. And we can play a couple more tricks here. Now, how do we manipulate this magnetic field? One way is we can link many of these loops together, like shown at the right here. This is what's referred to as a solenoid. So just a bunch of loops, loop, 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 together, current continuing to flow down there, and that's going to create a magnetic field now that's not necessarily much larger, but it's very long. So now we have a magnetic field that's going to be big enough to create, for example, like our B0, our main magnetic field. We can stick a person inside this. This is how a solenoid-like configuration is what is used for our main B0 magnet. Then the other thing we want to be able to do is, well, how do we create larger magnetic fields? So in the last lecture, I mentioned that the larger the magnetic field, the higher the signal that we're going to get. And the main mechanism that we use to do this for the B0 field is to create much larger currents, so represented by the larger I in this picture, which is going to lead to larger magnetic fields. And the problem becomes with conventional wires, copper wires. Eventually you can only feed so much current into them without melting the wires. So the solution to this is what's called superconducting, create a superconducting magnet. And this is done by taking specialized materials, often like this alloy, niobium, titanium. You immerse this in liquid helium, which is 4 degrees Kelvin, so 4 degrees above absolute zero. And under these conditions, these materials become what are called superconductive. So they have basically zero resistance, which allows us to put extremely high currents. So we're going to make a loops of this niobium titanium wire. We're going to put it in a bunch of liquid helium, get it very cold, get it into the superconducting condition, and then we can throw a whole bunch of current into these loops of wire and create these very large magnetic fields that we typically use for MRI. Another way that we'll look at the magnetic field is the amplitude. And we try to make the magnet itself so that the magnetic field is homogeneous or the same where we're trying to create an image. But then it's going to drop away as we go farther away from the MRI system itself. So there'll be, and for a safety concern, we'll think about what is the magnetic field as we go away from our main magnetic field. Something like the 5 Gauss line will be a term that you may hear. So now we're going to switch gears to talk about the magnetic fields created and also detected by RF coils. And this slide is just repeated from the previous lecture, but just a refresher that, remember, we have 2 purposes of our RF coils. We have excitation, represented in green in this cartoon, where this is where we're actually creating a magnetic field because through our RF coils to transmit RF energy into the subject, create this perturbation of the net magnetization such that we can receive signal. And that's then the second purpose of RF coils, is that the net magnetization rotating creates these oscillating magnetic fields that then in our RF coils we're trying to detect these changing magnetic fields, and the oscillating magnetic fields create currents in the receive RF coils. Okay, and we'll go into a little more detail about the mechanism by which this occurs. So I want to move on and talk a little bit about then the RF coils, and these operate under the same principles as our loop coils. We're going to, for a transmit RF coil, what we're going to do is we're going to put a current into wires to create magnetic fields. So this is our bird cage design sitting around a head. Here's a cross-sectional view of that, where the X's and pluses here indicate current going in and out of the slide. And as in this case, it's current going into the slide, because we can use in the right-hand rule to say current. Now we use it now as a current going in one way is going to create a magnetic field going in the perpendicular plane. And so what we can do is run current through these wires and create, each one of them creates their own magnetic field here. And and so we create this, and now this is a magnetic field. So current running through all these wires, that's a magnetic field that's pointing in this direction. And our B0 field is pointing perpendicular to that for reasons that we'll go into much more detail into later. But it's still operating under the same electromagnetic principle of currents in a wire are going to create a magnetic field. So that's our transmit coil. Then we can actually translate that understanding directly back to the receive coils by this principle called reciprocity. That means the principles of magnetic field generation via currents apply to currents that are generated from magnetic fields. Okay, so if a current creates a given magnetic field, then if we have that given magnetic field change happening, we'll create the same current that we did before. So this means we can apply our same sort of RF coil profile to either looking at how it behaves during transmit, so when we're putting current into the coil, or how it's behaving during receive in transmit we're creating rotating magnetic fields, in receive we're trying to measure rotating magnetic fields. So just repeating the same profile here, except now my drawing in the middle here has changed. Before it said B1, meaning that's the RF magnetic field we create. We're creating an RF magnetic field that was rotating around. Now what's happening is the net magnetization is rotating around, and when it rotates around, it's going to create currents in all of these wires that we can measure. And finally, I want to talk about the coil profile of one of our most common RF coil configurations used all the time in receive arrays, which is a simple loop of wire. So the birdcage I just showed is a little more complex. This is a simple loop where current is coming in around this coil and creating a magnetic field, I guess like that. And these are the equivalent magnetic field lines here that are being shown, that are created by this current in the wire. So if you look in the GitHub repository that's linked to at the Corf website, there's the code that is used to generate these simulations here. And here we're simulating this loop of wire and the magnetic field that it creates. Note in these plots, the wire is first shown in the YZ plane, and then the rest of the plots have been flipped sideways, so the coil is actually sitting right here. We're looking at a cross-sectional view, and this first plot is actually showing the magnetic field vectors. Recall from the beginning, the magnetic field is a vector field. It has a direction and an amplitude existing everywhere in space. These vectors are larger, closer to the coil. They become much smaller, further away, and particularly near the wire itself, they tend to have more of a divergent pattern, more and more angle to them. And then the other three plots are simply showing various components of that magnetic field vector. So showing the total magnitude of the magnetic field here, getting smaller and smaller as we get away from the coil, being larger right next to the wires, and then the splitting out here both the X and the Y component of this magnetic field as well here. And that's it for this supplement. I hope some of that was helpful and interesting for you. Thanks.